Hello, my name is Cable Warren, and I will be presenting my research into fast Fourier transform, or FFT, as an analysis method for chromatographic peak identification confirmation. The goal of peak identification confirmation is rooted in an industrial setting. Industry standard for chromatographic peak identification is based almost solely on retention time matching, where retention times of unknown peaks are compared to those of standards. However, this method is not able to account for compounds that elute within the same retention time windows close to each other, whether or not they elute on top of each other, or peaks with small impurities that don't have a great effect on retention time. So peak identification confirmation can help to differentiate between pure compounds and to root out these impurities. And so before I get into the data, it's important to understand the basic concept of Fourier transform. FFT takes data from its original domain, whether it be volume or time in the case of chromatography, and converts it into the frequency domain. The data is broken down from a raw form into component sine waves of different frequencies and intensities, which are all then gathered and reported as a frequency distribution. So we hypothesize that these distributions are significantly different between analytes, such that they can be used to confirm or deny the identity of an unknown peak based on its frequency distribution. And so the reasoning behind this comes from previous work done in the dust group to group, utilizing peak shape as a method of identification confirmation. The idea was that different analytes and mixtures thereof provide measurably different peak shapes, and that they change predictably with sample volume or peak area. So to show this, standards were run at various concentrations, and the peak shapes were recorded over a various range of peak areas. Then shape calibration matrices, as we call them, were produced using different recorded peak shapes and allowed for the production of theoretical peaks for any analyte at any specific area. So these predicted peaks, as they were produced and compared to unknown peaks at the same peak area. You can see this here as an example comparing two unknown peaks to predicted fluoride peaks at the same peak area. These peaks are normalized and plotted such that their maxima lie at 0 in time, and then their widths are measured all the way down at specified height intervals, and then compared to determine the sameness of these peaks. The metric was dubbed the index of width mismatch, or IWM, and it is a percentage measurement. And so for peaks to be considered the same, 99% of the measured widths need to be less than 1% different from each other. So the metric actually turned out to be a very accurate method of identification confirmation, with no false positives or negatives observed in this study. So then moving on to the FFT analysis, our hypothesis was then, since peak shapes are distinct enough to determine identification confirmation, so too should the fundamental frequencies that make up the peaks, as these frequencies are what determine the peak shape. So by comparing the frequency distributions generated by FFT, we hope to find an alternative, possibly easier method of identification confirmation. The work done so far has been to confirm the viability of this method for peak identification using the same basic scheme as the peak shape study. So FFTs were run on bromate and chloride standards at various concentrations to create the same matrices as in the peak shape study. These then allowed for the prediction of their frequency distributions at different peak areas. And so comparing these distributions to a range of concentrations of pure bromate and pure chloride, as well as a few controlled mixtures of the two, the differences between the chloride and the bromate were measured. The resulting IWM measurements were able to accurately distinguish between pure bromate and pure chloride, as well as mixtures that were almost pure. So you can easily tell the difference between the pure stuff and tell that the mixtures are not pure. And so it is yet to be seen if this method provides more accurate identification confirmation, or if there's an easier method than IWM in the frequency domain. However, as it stands, the IWM results are very encouraging toward the potential of this method, and it definitely warrants further study to quantify the computational burden of this method compared to the previous method, as well as to investigate whether or not there are other metrics besides IWM in the frequency domain that will allow us to determine the identity of these compounds. And so with that, I will let you go. Thank you for your attention.